right, so for recording purposes, today is the theory part of waves. And the first thing I just want to go through is what exactly is a wave? And a lot of people might know the definition of a wave, and it's on top here. But even before I read this definition, most people will read that definition, memorize it, and they have no idea what it actually means. Now, when most people see a wave, like the most popular example of a wave is when you go to the beach. Let's say you go to Maracas Beach and you see the water waves. And we know most waves, not all waves, but the majority of waves go up and down, up and down. Okay, like this, it goes up and down. The water waves go just like this, and you play in the waves and whatnot, right? Now, do you see water is something physical, and water is something we can see with our eyes. So, when you see the water waves moving up and down, you think waves is about particles because water is a particle. So initially you might say, well, waves has something to do with particles probably moving up and down, or sometimes you see the water coming towards you. The water waves come towards you. So that gives you the impression that the particles, the water waves, are actually coming towards you. But then you realize when you start to do physics, is that waves is not really about particles, you know. It's about energy. Now, energy and particles are completely different. Particles, you can what? Hold it in your hands, like water, even dust, even soil. But energy is not something you can hold. You can only feel the effects of energy. And also energy is measured in what? Joules. Let's make a wave. Other than a water wave, let's create a wave in the ground. So here we have a make-believe scenario. It have two boys here. It have a ball here, and it have a caterpillar that's inside the soil. The boys are too lazy to get the ball. So they tell the mammoth to stamp really, really hard on the ground. So the mammoth is going to stamp really, really hard on the ground, and let's see what will happen, right? He will create a wave, right? So let me get a thicker one here. He's going to create a wave like this. So you can imagine that I should have done that, but that's not one second. All right. So he creates a wave. So he disturbs the ground, right? So the ground begins to shake. Part of the ground goes up and part of the ground goes what? Down. Tell me something. Will the ball reach the two boys? Remember, it stamped the ground and the wave went this way. Will the ball eventually end up by the two boys? Well, what do you guys think? Will their plan work? You see what a wave is? A wave is actually the transfer of energy. You see the actual particles that make up the soil? They don't actually move forward, you know, the particles that make up the soil. The particles that make up the soil only go up and down. They only go up and down. In other words, the ball will just, like over here, the ball might just rise a little bit, but it will rise vertically and then it will go downwards vertically. You see, the particles itself are not actually moving forward. All it does, it disturbs as the energy moves through the soil. Everything that gets in the way of the energy gets displaced up or down. But the energy actually moves forward. not the actual particles. So that means the ball doesn't reach the boys, and the caterpillar who's mixed up in the soil doesn't go by the boys. He only moves what? Up and down. Only the energy actually moves from one point to the next point. In other words, the energy is the one that moves. The particles don't actually move back or forth. The particles are not actually transported anywhere. And that is what this definition is actually saying. And if you do this experiment in the ocean, and I'm not talking about the shallow part of the earth, of the beach works a little bit different, right? But if you go in the deep part of the ocean, right, and you put a ball in one part of the ocean, if you provided it have no hurricanes and whatnot, if you come back the next day, the ball is supposed to be in the same exact spot, even though you're seeing waves in the ocean. So everyone take down this definition. There's no need to take time to draw the diagram. Just take down the definition. What is a wave? And the definition below. There is a difference between the word transport and movement. Tell me something. Are the particles experiencing movement? Yes or no? The particles in the soil or the soccer ball or the caterpillar. Right. They are experiencing movement. They're moving up and down. Transport kind of hints that it's actually moving forward horizontally. So the better word to use is transporter, right? There is no movement. Sorry, there is no transport of matter, but there is movement. So the energy experiences, I just wanted to explain that difference, right? So the energy definitely experiences movement and transporter because it's moving from one point to the other. Right? This what somebody had a question there, so I just wanted. Right. So on the syllabus itself, right, it have a few definitions of the different types of waves. It have one called a pulse, a periodic wave, a progressive wave, a transverse wave, and a longitudinal wave. Now, I don't have a diagram for the transverse wave and the longitudinal wave on this slide, but it will be on the next slide. So let me explain these three. I'll give you a chance to take down everything else after, and we'll move on to the next slide. A pulse is a single wave. But look at this guy here. This here is the diagram for a pulse. He ties a rope to a post, and he just gives it one flick. Now, if he gives it one flick, you will see the hoop, well, exactly one hoop moving forward. And once that reaches the post, it dies out. That's a pulse, just one wave, and it never repeats itself ever again. However, if a person ties a rope to a tree, like this boy here, and he flicks his hand up and down continuously, he doesn't do it once, won't you see the same pattern occurring over and over and over and over? You call that a periodic wave. A periodic wave is a category of waves that happens over and over and over and over. It's not single. And a progressive wave, which is the type of waves that are on the syllabus, right? You see, when you produce the wave, right, you notice that the energy, you could see the energy moving away from the source. The source is the person creating the wave. Like in the first case here, the man is the source. He created the wave. And when he flicks his hand, even if he does it once, you can see the energy moving away from the man. You call that a progressive wave, where the energy moves away from the source. This one with the boy also, the boy is the source, and you will see the waves going this way, that means the energy is going through the medium away from the source. Okay? So, and of course, I have to explain what a transverse wave is and what a longitudinal wave is, but I need diagrams for that. Do me a favor, take down all 5 things here, right? If you want to draw the diagram of the pulse, feel free. And if you want to draw the diagram of the periodic wave, feel free. But it's not really too necessary once you understand it. Okay. Now, these are standard definitions that will come in your exam. Standard definition with 1 mark or 2 marks, depending. Let me know when you finish. I'll give you a full 5 minutes. Right, so here's the longitudinal waves versus the transverse wave. Now, you gotta keep in mind, in all of these diagrams, the energy is moving forward, right? We're gonna assume that something over here is causing like a disturbance. So a transverse wave is the easiest one to imagine. It's the one that we see in everyday life, like water waves, right? So remember, the water waves goes up and down. But how is the energy being transferred? Let me get a different color. How is the energy being transferred in a case like this? Remember, even though the water particles are going up and down, the energy is moving what? Forward. Okay? Now, look at it. If it is called the movement of the particles, the displacement, right? Right? That's one way, right? But you can call it the movement of the particles. Notice, look at the pink arrow. The pink arrow is moving up and down, but the green arrow represents what? The energy. You notice the angle between the pink arrow and the green arrow? It's how much degrees? 90 degrees. In other words, perpendicular. So in a transverse wave, the particles versus the energy are perpendicular. Hence this definition for longitudinal waves. And like I said, that's the easiest kind of waves because we see it every day. However, the less popular one is like the longitudinal waves. That's the underneath one. It's like air. I know we can't see air, but if you put a gas in the air or a dye in the air, like you make the air red, and you speak, do you know how sound reaches from my mouth to someone else's ears? When I talk, the energy from me talking causes the air to be compressed and decompressed, compressed and decompressed until, and it moves forward, compressing and decompressing the air until it reaches the person's ears. So look at it here. You have compressions and refractions. The compressions and decompressions. They don't call it decompressions, it's called it refractions. Look at it here. The lines are supposed to simulate how compressed or how close the particles are or how far the particles are. You notice that, let me get a different color so it's easy to see. You notice the air particles are being compressed or decompressed. But the energy, which is the green line here, is still moving forward. Now look at the green line and look at what? The pink arrows. They are not perpendicular. They are actually what? Parallel. Both of them horizontal, right? Hence the definition for longitudinal waves. And the most common example for a longitudinal wave is sound. Sound compresses and decompresses. It doesn't make the air particles go up and down like in a transverse wave, right? Now, I know you all are probably, oh God, I have to draw this and whatnot. Yes, guys. And I want you to draw in, yeah, just draw. And if you want to take down my green lines and whatnot to show the direction of the energy to update your diagrams, feel free, right? Let us write the word energy here. right? Take our 5 minutes, draw it out properly, and take down the definitions. All right, so this is where the fun begins a little bit here, guys. So it's you all versus me. So what's going to happen? Each of these treasure chests has like money and stuff and things like that, right? So the class is going to vote which treasure chest you all want for the class. The most popular vote goes to the class. The least popular, whichever one you all vote least on, but the least popular one, I will get. So it's not like I could choose whichever one I want, so I can't cheat. Okay? Anyway, let's go. Let's vote. Which one should we? You all vote on which one you all want to. Let's see. Let's launch the polls here. Begin to vote there, guys. Let's see. All right, so it seems that the most popular one here is which one here? Let me go down. Is G. G is the most popular one. Which one is the least popular one here, guys? Which one is the least popular one? I think it's D, if I'm not mistaken. Help me out there. Which one looking like the least popular one? It's D. All right, so that means you guys get G and I get D. All right, so let's go. Stop sharing. All right, so let's see what each one has here. The first one is $800. I get which one? D. So I get $500. I'm putting on my $500. And you all get D. Oh, G gets nothing. You lose all the money that you had, but you had $0. So when you lose the $0, you'll end up with 0. So far, guys, I am ahead. C is what you call multiply by 3. If whatever money you had, you would multiply by 3. So if you had like a $200 before, you would have $600. So I'm ahead. Don't worry. Hopefully you guys will be ahead of me in the next room. All right. So when it comes to waves, there are two different categories of waves, right? There are two different categories. It have mechanical waves, which require something called a medium. A medium is like a substance. So longitudinal waves and transverse waves, like sound waves and water waves that we discussed just now, for the energy to flow through, it needs a medium, it needs an actual substance in order to flow from one point to the next point. So you call those mechanical waves. The opposite of a mechanical wave is something called an electromagnetic wave. Now, electromagnetic waves do not require a medium. And these are some examples: light, microwaves, infrared. I'm sure you hear about plenty of these things here. But let's talk about light. Light is a type of energy, and it actually travels in the form of a wave. Now, light falls under electromagnetic waves, and we said that they do not require a medium. And I could prove that to you all. The sun, let's draw the sun here. The sun is in space. So this here is the sun, shining, 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 right? We all know light from the sun reaches the earth. So let me draw the earth here. That get a little nice green dot here. So this is the earth here. So light travels from the sun to the earth, right? Is there any substance between the sun and the earth? Is there water, a big chunk of water between the sun and the earth? Is there any air between connecting the sun to the earth? The answer is no. So this is kind of like proof. Light, which is a type of electromagnetic wave, which we'll study in detail much later, right? Does not need a medium. The energy still manages to reach from the sun to the earth without any substance linking them directly, right? And all of these guys here, the microwaves, the infrared, X-rays and whatnot. By the way, the sun doesn't only produce light, the sun actually produces infrared and some X-rays and ultraviolet rays, right? And all of those things manage to reach from the sun all the way to the earth, right? As far as I know, the sun doesn't produce radio waves and microwaves. If it does, it's probably so little bit. It's not even worth the discussion. So draw that little, what you call this, I guess, a little flow chart there that shows you the two categories of waves and the examples to go with it, right? So remember, when you're discussing waves, it's either going to be a mechanical wave or an electromagnetic wave. Let me know when you guys are finished. Right, let's see what the next slide is about. So here we have the difference. This is a real big part of the syllabus, right? They like you to compare the differences between a transverse wave and a longitudinal wave. Now, one of them is no longer on the syllabus. So that was number 5 here, but you could see that I edited it out. So you could call the last one here number 5, right? So I'm just going to edit it here for you guys here, right? Right. If you don't know what a crest and a trough is, let me just explain what this is. Remember how a transverse wave is depicted, right? Normally, it's depicted as ups and downs, ups and downs, okay? The actual top of the wave is called the crest, right? The lowest part of the transverse wave, this is transverse waves, is called the trough. Now, longitudinal waves don't have that. They don't have ups and downs. Remember, longitudinal waves are either compressed or decompressed. Compressed and decompressed. Now, we don't usually say decompressed. The compression part is when you squeeze the particles together, and the rarefactions is when it's decompressed. In other words, when the particles are spaced out more. But remember, in a transverse wave, the displacement and the direction of the wave are at right angles. That was key. And in a longitudinal wave, the displacement of the particles and the transfer of the energy are parallel, right? And it's easy to imagine that in a longitudinal wave, the compressions will cause what? An increase in pressure. It comes like somebody squeezing something on you or squeezing you together. The pressure will be more. And of course, when the particles are spaced out more, there is less pressure. So longitudinal waves create a pressure difference when it is moving through the medium. All right, so I just wanted, most of the times when I teach that topic, that's the two most common questions I get. So I just kind of answer it one time. Right. Sorry for the amount of notes, but it is necessary because you get a ton of questions in the exam on this particular, not ton, but let me call it 2 to 3 questions, which is still a lot. All right, let's get ready to go. Let's see what the next slide is about. All right, so after all that writing, keep track of how much money you guys have. It shouldn't be too hard for you guys because you guys have $0. Why I have $500, right? Let's vote one more. Let's vote another time, and let's see if you guys get a little bit. Begin your vote. Let's see which one is the most popular and which one is the least popular. Remember, I get the least popular vote, you get the most popular. And poll share results. It seems that there is a tie between C and F. All right, so to be fair, you all will get 2, C and F, right? And now, if for C and F, if one is bad and one is good, you will take the good option. So whichever one is better, you all will use that one. Which one is the least popular one here? It would be D. So I am getting. Let's go. A, B, C, D, E, F, and G. So, like we said, you guys are getting what? C and F. This is C, and we're F. So, remember I told you also there's a tie. You choose the better of the 2 options. So you all put down $600. You all get $600, and I get D. D is just a mere $100. So look at that. We have the same amount of money now. I had 500 from before, and I have what? $100 now. And you all just got $600. So we tie in right. Keep tracking, guys. Keep track. You know how I like to cheat, right? So I try to cheat. Right. Now, you have to know the diagram of a transverse wave, right? It's real important, right? So I already mentioned, right? You don't have a detailed diagram as yet. However, the top of the wave, this is a transverse wave actually. The top of a wave is called the crest. Now, don't mix it up with the amplitude. A lot of people are going to mix up the crest with the amplitude. Let me just give you some values here. Let's put an X and a Y axis here, right? Let's get an X and a Y axis here. So if this is the Y axis, right? Let's say this is a water wave. Let here be 5 meters, right? So the wave is going up to 5 meters. The crest is just the top of the wave. It doesn't have a value. It's just like you're surfing and somebody asks you where you are. And if you are at the highest point of the wave, well, then you say you're just on the crest. You don't call the value. The amplitude, on the other hand, has a value. The amplitude would be 5 meters. So the amplitude is like the maximum displacement, the value of the maximum displacement from the rest position is the middle, to the crest. But the amplitude you call the value. So that is a subtle difference, but it's very important in the exam. And the trough is the actual lowest point. It doesn't really have a value, okay? And a wavelength is the distance between 2 consecutive similar points. So if you measure the distance from one crest to the actual next crest, that would be the wavelength. So let me just assume the wavelength here is 7 meters. However, if you measure the distance between 2 consecutive troughs, now my trough is a similar point, and our next trough is a similar point, but it's the one that comes right after, you will still get 7 meters. Also, if I take wood, I'm going to put 2 slashes here. I'm going to get 2 different colors here. Would the distance between this slash and this slash also be considered a wavelength? Are those 2 similar points? 2 consecutive similar points. If I measure the distance between the 2 blue slashes, would I also get 7 meters for the length of the wave, the wavelength? Well, first of all, you could use your eyes and see, well, That cannot be 7 meters, right? The 7 meters, when they compare it to the rest of the diagram, that cannot be 7 meters. But doesn't that look like two similar points? Now, if you observe this properly, this is not two similar points. Let me explain why. Let me draw some arrows here. Pretend you have the wave like this. So the wave going up, 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 then it starts to go what? Down. And it goes like this. So it's following like this. So you can imagine those things, right? Now look at it. I'm going to call this point A and I'm going to call this point B. Now A and B look like it's similar, but look at it. Isn't the energy flowing downwards by A and by B when it crosses B, it going upwards? So that cannot be similar. That to me is the opposite of similar. That is the opposite. A and B are actually opposites. Where would the next downward energy flow be that's similar to A, the next consecutive one? Won't it be somewhere here? Over here, the energy is flowing downwards. I mean, all of them have the same height, but at C, the energy is also going downwards. So that means if you were to measure the distance between A and C, you would get 7 meters as well. Okay? You would also get 7 meters, right? So this here is the diagram of a transverse wave, right? So I have to clear everything here because I know if you guys try to draw everything here with all of this annotations on it, it's going to be what? Too difficult, okay? Draw it properly, label it properly. Now, you know if you're going to get a diagram for the transverse wave, you know you're going to get one for the longitudinal wave, right? Can't get away from that. And here's the detailed one of the longitudinal wave. You can clearly see the compression and the decompression. Now, for the longitudinal wave, to keep things easier, the wavelength will either be between two successive compressions or the middle of two consecutive refractions. Okay? Refractions, sorry, not fractions, right? So this one is a little bit easier because to find in between similar points on a longitudinal wave, you have to have a real good eye. I don't have a real good eye. Okay? So take down this one, right? So 2 minutes max for this one, right? Oops, sorry. Let's have a look at this here. So you see two graphs. Now here's the thing, right? Not because the graphs are going up and down means it's a transverse wave that we are recording. A graph, remember, there's a big difference between a graph and a physical drawing of how the wave looks in real life. A graph depicts certain properties of something in real life, okay? Not because the shape of the graph is a certain way, it means that it looks like that in real life. Now, sometimes the graph just happens to look like something, look like the thing in real life, but that's just a coincidence, okay? So here are two graphs, right? Let me put some values here. Let's say we're measuring a water wave. Let's just keep it simple and let's just pretend it's a transverse wave. So let's say over here is the height of the wave. So height. And it's going to be in meters. So we're measuring the height in meters. Let's say here is 8 meters and below here is minus 8 meters. Right? I'm going to put some measurements here. Right. Let's say this value here is 25 meters. And the next graph here, almost the same thing. We're going to put 8 meters here, and we're going to put minus 8 meters. And let's put the time here. I'm going to put it in seconds as, let's call it 50 seconds. Right. I want you all to tell me the wavelength. What's the wave? Now, we're going to assume that these two graphs represent the same wave. So we take two different types of measurements, and for the same wave, we draw two different graphs to represent what's going on in the wave. Who can tell me what's the wave length? What is the wave length? Figure out which graph you need to use. You can't use any graph. Look at the two graphs and figure out which graph is the correct one, teacher. Now, we're looking for wave length. So we have to choose the graph where the x-axis measures the length. You notice one measures the length of the wave and the other one measures time. We can't use time to measure length, so we have to use the first graph. Now, what is the wavelength? A wavelength is the distance between two similar points. Remember the graph over here, the wave is going up and then it's going down and then it's going up again. Isn't A and E similar points? In other words, in most cases, a wavelength consists of one up and exactly one down, or the distance between two crests, or the distance between two troughs. But one going up and another point also going up would also be considered a wavelength. So the wavelength, the easiest way is to find the distance between A and E. If you have notice you have two wavelengths here, right? Two oscillations. Oscillations is basically one wavelength. If from here to here is 25, any middle here will be 12.5. Does that make sense? Because it's half, right? So the wavelength is actually 12.5 meters. The second one, if they ask you for the periodic time is the time taken for one oscillation. An oscillation is basically one up and one down. Now, if I ask you for the periodic time, you cannot watch the first graph. You have to watch what? The second graph. So the periodic time would be 25 seconds. You have to look at the second graph. You see, but both of these represent the same wave. It's just both graphs are extracting different information off the same wave, right? Because I realized someone said the wavelength was 25. They just took 50 and divided by 2. But this axis represents time. You can't convert time to length. And here's what, guys. You all should be able, for those who did the homework, calculate the frequency for me. Ask yourself, what's the formula to calculate frequency? You have all the information on the screen there. You should be able to do it, right? Remember, the formula to calculate frequency is 1 divided by the periodic time. That was a standard formula. So to calculate the frequency, the 1 always goes on top, and you always divide it by what? The periodic time, which is 25. And frequency is always measured in hertz. Capital H, comma Z. How much is 1 divided by 25? The answer, three people got it correct, 0.04. Come on, guys. This shows me that a lot of people didn't do the homework. Because that was a simple formula. One of the simplest formulas ever that was in the homework. The formula to calculate velocity of a wave, it's frequency multiplied by the wavelength. Now, you notice if I only gave you one graph, you won't be able to calculate what? The velocity. Because one graph, we were able to reason out the wavelength. The other graph, we were able to get the periodic time. And from the periodic time, we would calculate the frequency. So you actually need the two graphs in order to calculate the velocity for this particular question. So the frequency is 0.04 and the wavelength is how much? 12.5. Let's multiply it. 0.04 multiplied by 12.5, 0.5 meters per second. That's the answer. Right? Take down everything, and guys, take down everything. My annotations, everything. Let me know when you're finished. All right, let's vote. Let's go. Let's see who's the winner today.